Why are we interested in molten salt reactors? Okay. What happens in a molten salt reactor? That's a very special type of nuclear reactor. Why is it so special? It's special because the fuel is a molten salt. Okay? Now, historically, what was used is UF4. Okay? It's a very special form of uranium. Okay? Right? It's the 235 isotope of uranium tetrafluoride. Okay? This is a salt. You can melt that. You can melt that with, as I mentioned before, lithium fluoride dot beryllium difluoride. And the melting point of this, which is very high, and you can Google that, goes down. Another way, another salt that could be used is the very special isotope thorium. Thorium is, the isotope is 232. Okay? What happens? Thorium-232 is lying on the beaches of Long Island right now. It's lying on the beaches of Florida right now, and it's just kind of sitting there doing nothing. Because this is an extremely weak, it's radioactive, but it's extremely weak. The half-life of this is longer than the half-life of the universe. Okay? That's a very long time. And this is actually, the half-life of this is actually longer. Thorium-232 is actually another candidate that could be used in a molten salt reactor. It's similar to uranium-235, but it has some very interesting properties. Look what happens. You take the thorium-232, okay, which is just sitting there on like the beaches of Long Island where we are, or the beaches of Florida, or the alluvial deposits at the base of the Appalachian Mountains in the western part of North Carolina, or sitting underneath or very near the Rockies in Idaho. What happens with this thorium-232? Thorium-232 plus a neutron yields 233 uranium. 233 uranium is not equal to 235 uranium. They're not equal. Chemically, they're the same, but clearly these numbers are different, and that has a lot of significance. When you use this in the form of thorium tetrafluoride, and you whack it with that neutron, like above, goes to uranium tetrafluoride, right? And then that's the special one, 233, okay? This is actually what becomes fissile, okay? This is actually the fissile one, okay? The fact that it's 233 makes it special. It's much harder to get to plutonium-239, right? So we all know what this is, right? Plutonium-239, it's tougher to get here from here than here. And that's in large part what makes the difference. So when this goes fissile and decays, it gives off lots of energy, but it's tougher to get to here because you just got to keep going up in the periodic table. And this is a lot closer to this than this is. And that's how it goes. That's really it.